In this video, we're going to look at a slimmed down version of sections 5.1, 5.2, and 5.3. Change that there. Of so basically, we're covering trigonometric identities and formulas and looking at ways to simplify them, rewrite them. We've seen some already. For example, when we first started, we talked about the basic sine, cosine, and those things. We have the reciprocal identities. Sine and cosecant have a relationship. They are reciprocals of each other. And so we can see that sine is 1 over cosecant, but cosecant is 1 over sine. So we call those the reciprocal identities. You're familiar with those. And then we have the quotient identities, where we look at, well, tangent is made up of sine over cosine, and cotangent is made up of cosine over sine. In fact, if you think about it, all of these can be expressed in terms of sine and cosine. We looked at the Pythagorean identities, which is basically, these are derivatives of the Pythagorean theorem, where we get relationships with cotangent and cosecant, tangent, secant, sine, and cosine. And then we talked about the even and odd ones. The fact that sine is an odd identity. If we plug in a negative, we get the opposite. For cosine, if we plug in a negative, we get the same. So cosine is even, sine is odd. So tangent is odd, cosecant is odd. Secant, of course, because it has a relationship with cosine, is even. And so really they're all odd except for cosine and secant. So when we're looking to rewrite things, one of the things that we can do is to go back to the fact that most of these, all of these can be written in terms of sine and cosine. And sometimes playing around with these, rewriting them in those terms, can help us see ways that we can simplify this, rewrite them, etc. So if I rewrite this expression, and possibly I'm trying to combine all these together into one statement, one term, we can begin to see the relationships and what we can do as we look at them just from the standpoint of sine and cosine. So for example, cotangent is cosine over sine, and then tangent is sine over cosine, and then cosecant is 1 over sine, and secant, cosecant and then secant it has a relationship with cosine. Well, let's keep those as x. So if we were wanting to kind of write these together, we could start with the first two here. Say, all right, well, I've got sine and cosine. Let's create their denominators so that they're made up of, well, one sine and one cosine. So for these guys, we're going to make this cosine x, sine x, cosine x, sine x, getting a common denominator because we're trying to add them together. I can multiply the top and the bottom here by cosine. So that gives me a cosine squared x here. Here I need to multiply the top and the bottom by sine because I'm missing a sine in the denominator. That gives me sine squared x. And then over here, if we actually multiply that, we actually have the same denominator, cosine x, sine x. And 1 times 1 just gives me 1 on top. Writing all this together, we can put them as one fraction now because they all have the same denominator of cosine x, sine x. On the top, I have cosine squared x plus sine squared x plus 1. And I can actually see that here's a Pythagorean identity now. Cosine x plus sine squared x, is 1. We add those together. So now I have 1 plus 1 over cosine x sine x, which gives me 2 over cosine x sine x. I've put all of these into one fraction now, and I simplified the top by quite a bit. One fraction, there's nothing more I can do here really, cosine and sine. There's no identity that has sine times cosine, but we did see that, I had missing an x here, though the Pythagorean all of a sudden came into it here. These are the things we want to look for. We want to look for those relationships. One of the ways we can do it is by putting them in terms of sine and cosine. We can also look at proving theorems, where we're saying one side is equal to another side, or we can try to show how one side is not equal to the other side. Here's one common mistake that is made a lot of times, is distributing a square to a sum or a difference, right? To an addition or a subtraction. There's a few ways we can prove or disprove whether two things are equal to each other. One is to just start messing with one of them and seeing if we can get one side to be equal to the other side. And that's one way to do it. So if I took, for example, the sine minus cosine x, and I actually squared that, which means when we square something, we actually have to do the whole FOIL business. So writing this out, this would give me, sine squared x. We have our first. And then we have a minus sine x cosine x. That's for that one. Then we have another one of those, minus sine x cosine x. You could put those in either order. I just want them to look the same. And then we have the addition of cosine squared x. And we see these two in the middle are the same, so this gives me sine squared x minus 2 sine x cosine x. And then we have plus cosine squared x. And actually with these two, this would be sine squared x plus cosine squared x would give me 1. So this would end up simplifying down to 1 minus 2 sine x cosine x, which is not the same as sine squared x minus cosine squared x. In fact, the part of the sine and the cosine that we ended up with was actually being added, not being subtracted, because that we had a negative times a negative, so that became positive cosine squared x. So, I really can't simplify what I have over here anymore. I could try to maybe rewrite this over here, right? Maybe sine x as 1 minus cosine squared x using Pythagorean. Then we have minus cosine squared x here. So that would give me 1 minus 2 cosine squared x. But again, that doesn't... that's not the same as what I have on the other side. And no matter what I really do here, they're not going to be equal to each other. So eventually we come to the point of there's no equality here that I can achieve. Another way to do it is to put a number in there that shows you that one side is not equal to the other side. Because if they are an identity, we should be able to put anything in for x. One value that we can put in, remember thinking in terms of angles, either in radians or degrees, is 0. 0 is really nice and easy to work with. So for example, sine 0 minus cosine 0, and then square that and put the same thing on the other side. So sine squared 0 minus cosine squared 0. And then we simplify this down. We know that sine at 0 is 0. The y at 0 is 0. And then the x at 0 is 1. So this would be 0 minus 1 squared. And then sine squared 0, well, again, sine of 0 is 0, and we're going to square that, minus cosine of 0 is 1, which we're going to square that as well. 0 minus 1 over here would be negative 1. It's in parentheses squared. We're squaring the parentheses. But over here we have 0, and then we have a subtraction of 1 squared, which is 1. So we end up with a positive 1 over here, negative 1 over here. So we can see that these two expressions on either side, these two trigonometric expressions, do not signify an identity. This, in fact, is one of those do not do this rules that I always harp on my classes. X plus y plus or minus y squared does not equal x squared plus or minus y squared. I call this the do not do this list. Do not do this rule, because we don't do that. We can distribute it too if we're multiplying by 2, but a square like that does not distribute. What it will distribute to is a product. So if we have x times y squared, this does equal x squared y. Or if we have x over y squared, we apply that square, that's y squared too, to the top and to the bottom. So it works with multiplication and division, but not with addition and subtraction. So when we're trying to verify that one side is equal to the other side, the problem with the counterexample is that will only show that something is not an identity, right? But if you plug in one number into a identity, or at least something that's presented like you want to prove that it is an identity, showing that one number plugged in makes it work does not prove it. You need to be able to prove it for every possible plug-in that you would have. And that's, of course, impossible. So the way we verify trig identities is to transform one side of the equation. So when we have an identity, you've got it equals with one side and the other. We want to basically transform one side until it looks like the other side, right? And the steps that we may perform, they could be just algebraic manipulations, like we're adding two things together or subtracting two things together, getting common denominators, adding and subtracting, or multiplying them, or rewriting them using known identities, a bunch of which we went over at the very beginning. Note that in verifying an identity, we do not just perform the same operation on both sides of the equation. We're not trying to move things from one side to the other. Instead, what we're trying to do is to basically simplify the expressions, rewrite the expressions, hoping that by rewriting them, we can make one side look like the other side. All right, so here's an identity that we want to verify that it is indeed an identity. And so we're going to start with the left-hand side. Usually we want to start with the more complicated side and try to uncomplicate it. That's easier than trying to uncomplicate something that's simplified, right? So we're going to start with the left side. It looks like on the left we might have a Pythagorean identity. So we'll go back and look at our Pythagorean identities and see, aha, there is a relationship here between cosecant and cotangent. What we have is cosecant minus 1, or is that right? Yeah, cosecant squared minus 1. And what our previous one said is that the cotangent squared x plus 1, which is different than what we have here, is equal to cosecant squared. But I could rewrite this by solving it or getting the cotangent by itself. If I subtract 1 on both sides, we can see, indeed, there is a relationship here. Cotangent squared x is equal to cosecant squared x minus 1. And so I see that I can take this out and put cotangent squared x in its place. So that would give me cotangent squared x over cotangent x equaling cotangent. And here I see I can cancel out one of my cotangents. We have one down here. This is basically akin to like an x squared over x equaling x. Right, I take out one of the x's here, take away one from the power. In the same way we just showed on the left-hand side that we have cotangent x being equal to cotangent x on the other side. So we have now verified this identity. This is just a fancier way of writing cotangent x. Here's another one that we may want to try to, we're going to try to verify this identity. And it doesn't look like we have a whole lot to sort of work with here, right? But I'm going to start with the more complicated side, again, which would be on the left. And I'll write out things that I know. For example, I know secant has a relationship with cosine. It's equal to 1 over cosine. And then we have minus, this is cosine theta, which is cosine over 1. And this is sine theta down here. Let's see about combining those two on the top there. I think maybe if I combine them, I might be able to see something. So I'm going to do this off to the side here. 1 minus cosine theta. Let's get a common denominator. To do that, I've got to multiply, this is over 1, the top and the bottom by cosine. So that gives me cosine squared theta over cosine. So notice that I've just introduced another cosine on top. Cosine squared theta. Cosine on top and cosine on bottom. So that gives me cosine squared on top. And then writing these as 1, that gives me 1 minus cosine squared theta over just a regular cosine theta. All right, so I'm going to rewrite that in now. So I have 1 minus cosine squared theta over cosine theta over sine theta. 1 minus cosine squared theta that's a trig identity. That's a Pythagorean identity. Cosine squared theta plus sine squared theta is equal to 1. So if I subtract either of those two to the other side, I have the other one. So in this case, this can be rewritten. And I'm going to go ahead and erase this here for now. As sine squared theta over cosine theta. And then, of course, this is over sine theta. So we have kind of a complicated, complex fraction here. I'm going to take this top part, sine squared theta over cosine theta, and multiply it by the reciprocal of the bottom. This is sine theta over 1. So for dividing, it's the same as multiplying by the reciprocal. So 1 over sine theta. And this sine will cancel with one of those two sines. That leaves me with sine theta over cosine theta, which is what I was after here. I wanted sine theta over cosine theta for my final answer. So I proved or I verified this identity. Now, your head may be swimming as you go through this stuff, but there's just things that you need to try, right? And so there's some creativity that comes here, and you're like, well, let's try this or let's try that and see what we can figure out. Some of these, as you look at them, you're like, these don't look alike at all. I don't even know where to start. Well, for one, we can notice that we've got an addition here, right? And we've got a multiplication here. So one thing that we do a lot of is kind of, all right, let's actually carry out this addition. So I have cotangent to the fourth x plus cotangent squared x. I'm going to rewrite this as sine and cosine. And this is so we can get an idea of what we need to do to actually add these together. So I'm moving this over here to the left. And we're starting with the left. More complicated, right? We know that doing an addition is a little more complicated, right? So cotangent, remember, is cosine. So this is cosine to the fourth x over sine to the fourth x. And we're trying to add to that another cotangent, but it's cotangent squared x. Sorry, we don't want that. We want cosine. We're rewriting it. So cosine squared x over sine squared x. And so what I would need to do is to multiply the top and the bottom here. We need a common denominator by a couple more signs. So I need to multiply by sine squared x on top and bottom to make this sine to the fourth x. So now I have cosine squared x sine squared x over sine to the fourth x, which now matches with what I have over here, cosine to the fourth x. Oops, that's not 4x. That looks a little too like 4 times x. So I'm going to rewrite that. To the fourth x. Notice that it's different. When we say, I just want an aside over here. I take things for granted sometimes. But writing cosine squared x and cosine x squared is two different things. Here we would be taking the cosine of something that we square. But here we are taking the cosine of x and we're squaring it. So really what this means is cosine of x, parentheses, squared. All right, it's just a simpler way of doing it without having to put parentheses every time. We're squaring the cosine. Cosine is not a number. Cosine is an operation. So that says square the operation of your cosine. Okay. So that's just a little side there. And this is sine to the fourth x. So we have matching denominators. Let's go ahead and write these as one single fraction with one sine to the fourth x on bottom. I have cosine to the fourth x plus cosine squared x sine squared x. And I notice here that both of these have a cosine, at least two cosine squared x's. So one other thing I might do is to factor that out. If I factor that out, that gives me cosine squared x times cosine squared x plus sine squared x. Right? I took out two cosines here, two cosines there, two cosines, cosine squareds, from each side of that plus, which gave us this, and this is still over sine to the fourth well, cosine squared x plus sine squared x, that's 1. So I just found a major way to kind of simplify this. This is equal to 1. So really I can rewrite this now, and I'm going to put it up higher here so I'm just running out of room, as just cosine squared x over sine to the fourth x. Now sometimes you may want to really go back and kind of compare, like, where are we at now, Because what I want here is cotangent squared x times cosecant squared x. And these still don't look the same. I have one that's a fraction, one that's not a fraction. But if we look at what this is in terms of writing it with sine and cosine, cotangent would be cosine squared x over sine squared x, and cosecant squared x is 1 over sine squared x. Sorry, this is sine squared x too. Notice that if I actually carried out this operation, this would give me cosine squared x over sine to the fourth x. So they really are equal to each other. I can break this into cosine squared x over sine squared x times sine squared x, right? And this you could put as times 1. So see how this could be written as cotangent x squared, cotangent squared x, times 1 over sine squared is cosecant squared x. So they were, sometimes you can work with the other side as well if you kind of come to a place. Say, okay, well, let's relook at the other side. Is there a way to look at that in a different way? But eventually we got to one side being equal to exactly looking like the other side. And that's what we want to do. So you don't have to necessarily stick with one side and keep transforming that one side. You can choose to go over to the other side and start working on that one and see if you can make some progress there. Sometimes that's necessary. So here again, the more complicated side, I'm going to look at stuff that can be added or subtracted. This is all in one fraction. So we hope sometimes just by adding them, getting common denominators and all that, we can have it look like the other side. So these are completely different. 1 minus sine x is totally different than 1 plus sine x. So really, I just need to multiply the first one by 1 plus sine x and multiply this other one by 1 minus sine x, which this is actually going to work out okay. I have to do the same thing on top and bottom. Because this is the product of two things that are a sum and a difference. So the same things being added and being subtracted, being multiplied. So the product, the multiplication of a sum and a difference of two things that are the same. And that's what we have here. So this would give me 1 plus sine x on top over, this is a difference of two squares. So that always gives us the difference of two perfect squares because the inners and outers cancel. We have 1 times 1, which is 1 squared. And then we have positive sine x plus negative sine x. And then positive sine times negative sine, so minus sine squared x. And that's going to be true on the other side too. Minus 1 times that is just 1 minus sine x over here. Over difference of two squares. So 1 minus sine squared x. And I can leave off the squared because 1 squared is 1. That means I just carried out that operation. Oops, put that back in there. Okay, now we'd want to add these together. Write them as 1. Notice that I'm subtracting that second. So 1 minus sine squared, we'll just leave that here. And so in order to do that correctly, I want to make sure I distribute this subtraction to both parts. So I want to subtract the positive 1 that's there, but I also want to subtract the negative sine x. So that gives me 1 plus negative 1, which is 0. But then we have sine plus sine, which is 2 sine x. We're adding those, we're not multiplying them. So 2 sine x. And on the bottom, what can I do with that? Well, 1 minus sine squared x is part of that Pythagorean again. So that can become cosine squared x. Oops, I don't know how I accidentally wrote 2 cosine x. I think I was thinking of the results above. And anyway, this is still 2 sine x. I just brought that down. But on the bottom, I have cosine squared x. And, well, I could write this. We could break up that cosine, right? Make it 2 sine x. And then on the bottom, have cosine x times cosine x. And that way, I have sine x over cosine, which would become tangent x. So 2 tangent x, that 2 just stays, with the top. And 1 over cosine is secant x. Now, this still doesn't look like the other side at all. So I'm going to rewrite it and try to simplify that side now and see if I can maybe get the other side to look like this side. So now I'm going to try to simplify the right-hand side. I know that we do have another Pythagorean identity involving tangent and secant. 1 plus tangent squared x equals secant squared x. And if we subtracted 1 to the other side, we can always mess around with those as well. But I can take this tangent squared x plus 1 and write it as another secant squared x. So that would give me secant squared x plus secant squared x on the top. We still have our cosecant x on the bottom. But that's adding those, we change the coefficient out front, so we have 2 secant squared x's. Right, so when we multiply, if this was a multiplication there, we could make them secant to the 4th, but we can't do that. We just changed what's on the outside. And we have this over cosecant x. So we have 1 cosecant x on the top, and we have 2 secant x's. I'm sorry, 1 cosecant x on the bottom, 2 secants on top. So what if I broke up those 2 secants and just wrote it as 2 secant x times secant x over a cosecant x down here. I'm trying to get to tangent times a secant. I already have a secant. Is secant over secant over cosecant, is that equal to a tangent? Let's look at what that is. Secant x over cosecant x. This is being divided, and I can break this up because it's all multiplication on top and then just, something on the bottom. So there's no additions or subtractions. You know that we can't break up fractions like this. But here I could rewrite this as this. This is the same thing, right? This is over 1, and so therefore they could be written as one fraction again. So I'm breaking this up to see if secant over cosecant, if that comes out to tangent. Let's look at secant. Secant is 1 over cosine x, and cosecant is 1 over sine x, which could be equal to 1 over cosine x times the reciprocal of the bottom, which would be sine x over 1, which would give me sine x over cosine x, which is tangent x. So yes, secant over cosecant is the same as tangent. And so we would have tangent times secant x with the 2 out front, which is the same as what I have over here. So many, many steps there took me, but I was able to verify one or the other. Again, playing around, looking for patterns, rewriting, and this really tests your algebra skills of simplification, right? Because it's like all these x's and y's, but instead we've got the words, tangent x, secant squared x. So we have to learn to simplify using the same rules we would with algebra, but with trigonometric functions. Here we have a pretty interesting one. We have cosine x over 1 plus sine x. It almost looks at first glance like we might have just flipped one and then said they're equal, which of course wouldn't really make sense. But the second one is actually 1 minus sine x, so it's not exactly just one being flipped. But somehow we want to see if there's a relationship here. So one of the things that we can do is to multiply the second fraction. We're going to start with the second with what we would call the conjugate. The conjugate is what, with 1 plus sine x, would give us a product of a sum and a difference. So in other words, multiplying the top and the bottom, rewriting this fraction as 1 minus sine x on top and bottom. This, of course, gives me that really handy 1 squared minus sine squared, or 1 minus sine squared x. And on top, we have cosine x, if I distribute the cosine, minus sine x cosine x. Now maybe I didn't want to distribute that. If I didn't, because I'm not seeing a whole lot of ways to go here, I'm just actually going to leave this as a undistributed thing. See what I have there. 1 minus sine x times cosine x. See, a lot of these, it's kind of some trial and error, right? And I kind of saw when I was making it more complicated, I kind of prefer it like this because at least, I don't know, I'm keeping them separate, seeing if I can notice anything. And I do notice something here. This is equal to, that's our Pythagorean identity again, cosine squared x is equal to that, and that leaves me with 1 minus sine x multiplied by cosine x. And since we have them in the form of a product, we can cancel it, right? This is this is one factor I have up here, and the other factor is the cosine x, and that can cancel with one of the factors of cosine x I have on the bottom, which leaves me with 1 minus sine x, something we wouldn't necessarily suspect would be equal to each other, but they are. 1 minus sine of x over cosine x. So what are some things that we did there? In all of those, one of the things we did was we did algebra operations, right? A lot of the times we were taking fractions that were not combined together yet and combined them by looking for common denominators and things like that. So half the time, that's what I was doing. I was literally doing algebraic work there. And the other thing that I was looking for was some of the trig identities. And so always looking for those. You can tell that in almost every one of these, the Pythagorean identity came into play. The very first one, we just used the reciprocal identities. We rewrote them in terms of sine and cosine. Now, you're not always going to find that to be helpful. Sometimes that doesn't seem to help at all. But combining fractions, carrying out the multiplications, getting common denominators, all those things, once we started doing those, we began to see one side begin to look like and have a relationship with the other side. We try to stay on one side, but if we get stuck, there's nothing wrong with also going over and messing with the other side a little bit. So, step-by-step ways or procedures we can use here. Number one, these are just some guidelines. Start with the more complicated side. Sometimes that's a matter of personal judgment, but a lot of times you're going to find that when you have addition on one side or subtraction, adding those things together is going to be the helpful thing to go. Putting them together into one statement. So if one side of an identity is more complex than the other side, it's generally helpful to start with the more complicated, simplify it before it becomes identical to the other side. Until, not before. And that just makes more sense. It's easier to simplify something more complicated down to something simpler than it is to work backwards and make something simpler into something more complicated. Also, as you're going, stay focused on the final expression. Going back and forth, thinking about patterns, looking at where you want to go, right? Where we're trying to go is trying to make it look how the other side looks. Some options we can use. One is to convert it to sine and sines, sine and cosines. We did that on the very first one. Sometimes that is helpful. Other times it is not, and you'll figure out when it's not. And then the other option is you can always work on both sides. So if you get stuck or we just get to a point where you're like, I'm not really sure how I'm going to move at this point, maybe you can start rewriting and playing with the other side. And then sometimes you'll have a epiphany and find your answer. One of the lesser known options that we have is to use the conjugates like we had on the other side. When we have a 1 plus sine x, a 1 minus sine x, rewriting those so that they are the conjugate. Basically, you multiply it by the opposite sign. So if it's a plus statement, write a minus statement. Right? These two are conjugates. These two are conjugates. If I had secant x plus tan x, I could multiply it by secant x minus tan x. And anyway, a lot of times this will take you to some of the Pythagorean identities when you multiply by the conjugates. In 5.2, we're going to look at the sum and difference formulas that we have for sine and for cosine. And for cosine, one of the reasons why we have these is we know we have those special known things for sine and cosine. 60 degrees or pi over 3. Those give us special things for cosine. 30, which is pi over 6. And then we have the 45 degrees, which is pi over 4. Then we have the 90s and the zeros and all the other ones. These produce exact values that we can use rather than these decimals that we have to round. So there are times where I can take the cosine of some angle and break that angle into a sum of two special angles, right? So if we have like the sine of an angle that's not a special angle, maybe we can express it as a sum or a difference of some of our special angles, right? 60 plus 30 is 90. 45 plus 30 is 75. 60 plus 45 is 105. So there's a lot of different angles that we can get by re-expressing them, not only as just a sum, but as a difference. And then once I have that difference, I can use the cosine and sine of the individual ones to rewrite it. And so we can rewrite angles other than 30, 60, and 45, and 90, and all those. We can write them in exact terms, rather than decimal terms. Let's take a look at an example. So we look, for example, at the cosine of pi over 12. Pi over 12 is not one of my known things, but we can write it as a difference of pi over 3 minus pi over 4. If you remember, pi over 3 is 60, pi over 4 is 45, so if I go 60 minus 45, that's 15. So pi over 12 is the equivalent of 15 degrees. 180 divided by 12, pi is 180, right? Actually gives me 15. So I'm going to rewrite, if I'm going to find the cosine of pi over 12, I can rewrite it as the cosine of pi over 3 minus pi over 4, and then use the cosine formula, which is our u and our v, right? So notice that the cosines, with the cosine formulas, we have cosine u, cosine v, sine u, sine v, and if we're subtracting, this becomes the opposite. If we're adding, it becomes the opposite. It becomes a subtraction. If you can look for these little patterns that can help you remember, oh yeah, the cosine, the sum and difference formulas for cosine, use cosine, they always use cosine first, and then they either subtract or add the sines of the two angles, and they do it the opposite of whatever we're doing. If we're doing a subtraction, we're finding the sum. If we're doing a sum, we're finding the subtraction. So keeping that as mind as I go through this, I don't have to constantly look back and go, I know I'm going to do the cosine of each. So this would be the cosine of pi over 3 times the cosine of pi over 4. And then I'm subtracting, so I know it's going to be the addition of sine of pi over 3 times the sine of pi over 4. Isn't that nice? And then we can just simplify each one of these. The cosine of pi over 3, that's the cosine of 60 degrees. That is 1/2. So this is 1/2 times root 2 over 2. The 45 is always root 2 over 2 for both sine and cosine. The sine of 60 degrees is root 3 over 2. Oops, root 3 over 2. We're going to multiply that by 1/2, root 2 over 2. The sine of pi over 4. And so this simplifies down to the root 2 over 4 plus root 3 times root 2 is root 6. We can just multiply those two numbers, put them under 1 over 4. So we see that the sine of pi over 2 is equal to the root of 2 plus the root of 6 over 4. Writing it as a single fraction there. We could get what the decimal equivalent is of that, but we actually have it in exact terms here. This is the cosine of pi over 12, which is 15 degrees. Let's try a different one. I'm going to do the cosine of 75 degrees, knowing that, and I have it in degrees now, but knowing that 30 plus 45 is 75. So I'm going to write this as a sum. 30 plus 45. And now we can use the sum function of cosine. So this is going to give me cosine 30, cosine 45. Opposite operation, it's plus here, so we're going to have minus there. And sine 30, sine 45. The cosine, the x of 30, this is square root of 3 over 2. And cosine of 45 is root 2 over 2. And the sine of 30 degrees, the y value is 1/2. And the sine of 45, again, root 2 over 2. So this gives me something very similar, square root of 6 over 4 minus square root of 2 over 4. Writing this as one fraction. Square root of 6 minus square root of 2, that's a 2, all over 4. So you can see it's somewhat similar to what we have up here. This is a sum of those two. This is a difference of those two with the square root of 6 out front. Notice that would be a larger number, so we're going to end up with something positive, which makes sense because 75 is in the first quadrant. We'd expect that outcome to be positive. I want to point out this kind of one sort of obvious rule that we have with sine and cosine here. With sine and cosine, we have 30 degrees, and then we have our 60 degrees. So this is 30, this is 60, and you know the radian equivalents. With sine, if we're on the unit circle here, and I didn't draw that very well, but here, if we look at where we are with the x, we're a little closer to the 1. Root 3 over 2 is a larger value than 1/2, so it's greater than 1/2. In other words, 1/2 is smaller than root 3 over 2. This is one thing that I picture in my mind. So at 30 degrees, we are at the larger number for x, root 3 over 2. And if you look up here at the y, we're about halfway to where the 1 would be if this keeps on going up. So we're at the half value for the y. And up here, they switch spots. The 1/2 now is down here, and the almost to 1 part is up there. So root 3 over 2 is in the y spot. So they switch spots. With that 90 degrees, if we take 30, notice that 90 minus 30 gives us 60 here. And if I go to 60, 90 minus 60 is 30. So we have 30 degrees here. So we have that relationship, right? Because 30 plus 60 is 90, and we have those other things showing how we get the similar things. Similar outcomes are just switching spots, right? Where the sine and the cosine. Keep that in mind as we look at now a set of identities. We call these the cofunction identities. There's a relationship between what we get for sine and what we get for cosine. And so hence you're going to see a relationship with what we get with secant and what we get with cosecant. Right? Cosecant is just a reciprocal of sine, and secant is just the reciprocal of cosine. Right? So these same relationships will carry over. So for example, taking, if these were in degrees, it'd be a little bit easier, but remember pi over 2 is 90. So whatever my thing is, let's say this is 30, or it would be pi over 6. Pi over 2 minus pi over 6, or 90 minus 30, gives me the cosine of 60. And the cosine of 60 is the same thing I get when the sine of 30. Right? The cosine, I'm just using this as an example, the cosine of 90 minus 30, which is the cosine of 60, is the same thing I get as the sine of whatever is being subtracted there, sine of 30. The sine of 30 is a half, and the cosine of 60 is a half. And this actually remains true for all the values within that first quadrant. And generally, it's true already, right? We're just talking about similar points with x and y. And so we have these identities. 90 minus whatever I'm taking, and the cosine of that will be equal to whatever the sine is for that same angle v. And then the opposite is true. Sine of that minus v is the same as cosine, and so therefore that works for secant and cosecant. And tangent and cotangent share that same relationship. They switch places, and you'll notice on the tables that you have that you see that, right? One would have a root 2 over, or root 3 over 2. The other has a 1/2. And then with the other angle, they switch spots. And it's always 90 minus that angle where we see that switch of spots and that relationship occurring. And this works for radians and for degrees. So both. We could even easily prove one of these using the others. Remember, tangent is just sine over cosine. So this would be the sine of this same angle, pi over 2 minus v, over cosine of that angle, pi over 2 minus v. That's what tangent is. It's sine over cosine of the same angle. Well, sine, we know, of pi over 2 minus v is cosine of the v. And the cosine of pi over 2 minus v is the sine of v. And cosine over sine, well, that's cotangent of v. So we can see how these are easily related to each other. We also have sum and difference formulas for sine. They're a little bit different, obviously, because sine is different than cosine. But we can look for some patterns. Remember, for cosine, it was always cosine, cosine, and then plus or minus sine, sine. Here, it's a mix of the two. We have sine u cosine v plus cosine v sine v. Cosine u sine v. So we have cosine of the first angle, sine of the first angle, cosine of the second. Same operation. If this is plus, this is plus. And then we have, instead of sine u, we do cosine u times sine v. For u minus v, now, of course, these could be done in any order because addition doesn't have any. So u and v could be written in any order. I can have 35 plus 40, or 30 plus 45, or 45 plus 30. Like, it doesn't matter. But with subtraction, order does matter. So here we really have to pay attention to what's the first angle and what's the second angle. So we'll take the sine and cosine of each angle in order, right? And then the cosine and the sine. So we're always taking sine first, just like these are the sine formulas, and our operations are matching. Okay, well, here's, this is an interesting example here. We're looking at these and going, well, these are not special angles. So immediately I'm kind of reaching for my calculator, right? But I'm also noticing that this is what we were just looking at. It's a sum of two things, where we took the sine first, then we took the cosine, and then we took the cosine of the same angle and the sine of the other angle. So this is the sine. This is the sum of. This is the sine sum formula. And if we look at these two angles, 63 and 27 give us something very special. 7 plus 3 is 10. That's a 9. So this is 90. So rather than trying to evaluate this, really what I know is going to work out here is that, I'm actually doing it the opposite way. Sine of 90 is equal to the sine of 63 plus 27. And I know what the sine of 90 is. The sine, or the y value, at 90 degrees is 1. So I see 1 is the sine of 63 times the cosine of 27 plus the cosine of 63 times the sine of 27. I know that I don't have to do all of this. I just already know what it's going to work out because I know what the sum of those two values is. They're 90. And the sine of 90 is easy. Okay, here we're given some information about u. We're not told what the actual measurement of u is, what the angle is. But we're told that sine u and cosine u equal these values here. And we want to find the exact value of sine of u plus v. Let's go ahead and just write out what we know. I'm going to ignore all the other stuff for a minute. I have some of this, so I'm just going to rewrite the sine formula. This is a sum, so it's going to be first sine, right, because it's a sine. So sine of u, cosine of v. We know that the operations match up, and then it's going to be the cosine of u, sine of v. Now, what do we know? We know the sine of u, so I can put that in. That's this spot. Sine of u, we already have that. Negative 3 over 5 is going to be times the cosine of v, which I don't know. Cosine of v is not given yet. And then the cosine of u, I'm given that, so this is 12/13, and then that's going to be times the sine of v. So the two things I need to figure out is what's the cosine of v and what is the sine of v. So we need to do some exploration of the angle v. I know that u was in the third quadrant. U is greater than pi but less than 3 pi over 2. Now this alone, the fact that it says that u is in the third quadrant, tells me there's something wrong with what I was given here. And so I had to actually go back and look it up. Because cosine, if u is in the third quadrant, both sine and cosine are negative. So cosine u here should be negative. So that's what I had to figure out. Is this the error? This is an error that the book had. Is this an error, or is the angle the error? And because either it's negative 12/13, or that isn't cosine u, it's cosine v. And that's what it's supposed to be. It's supposed to be cosine v. So they miswrote that. So let me figure out, let's rewrite what we have here. We actually don't know cosine of u. We know cosine of v. And cosine of v was 12/13. So we actually have half of this. This still is just cosine u sine of v. So we knew sine of u, and we knew cosine, not of u, but of cosine of v. So we knew these two. Now we need to figure out the other two. And they tell us what quadrant. This is the third quadrant, where they're both going to be negative. And this, 3 pi over 2 to 2 pi, this is the fourth quadrant, which means sine is positive, cosine is negative. I'm sorry, I said that backwards. Sine is negative, cosine is positive. All right, well, let's just take a look at one at a time here. We need to find cosine of u. So let's deal with u first. U, we know, is in the third quadrant. And we're told, it doesn't matter, we're not trying to find this per se. We're just trying to figure out what the cosine of that angle is. Because we need to know the cosine of u, but this is u. And we were told that the sine of u was 3 and 5, and that's opposite over hypotenuse. So -3, that makes sense because it's down below. And then 5 for my hypotenuse, opposite over hypotenuse. This is my 90. The cosine is going to be whatever this is over hypotenuse. And so we have 5 squared. That's my hypotenuse, equaling, we'll call it a squared plus -3 squared. So that gives me 25 is equal to a squared plus 9. And so a squared will be equal to 25 minus 9, which is 16. So a, in this case, is -4. And I know it's negative because I would have to go in a negative direction there to get to this spot. All right. So, plus we also know that in the third quadrant, cosine is negative. So, the cosine of u is the adjacent, so -4 over hypotenuse 5, so -4 over 5. Now let's go and find the sine of v. Fourth quadrant, and we're told that the cosine of v, so drawing my thing here, cosine is adjacent, so it's 3 over, I'm sorry, I'm doing the wrong ones here. We're doing v, and for cosine we had 12 over 13. Cosine is positive in the fourth quadrant, so that works out fine. And so that's 13 squared plus, or equals 12 squared plus b squared. And that's 169 equals 144 plus b squared. And 169 minus 144 is a lovely number. So subtracting 144 to the other side, we get 25 equaling b squared. And so b is equal to either positive or -5. And in this case, we know it's -5 because we're going down, right? And so the sine of v then, this is v. The sine of v is -5 over 13. So we have our sine, we have our cosine. I'm looking over here. Let's go ahead and write that in. The cosine of u was adjacent over hypotenuse, so -4 over 5, and the sine of v was -5 over 13. Can these be simplified at all? 3 doesn't go into 12, or 3 doesn't go into 13, 5 doesn't go into 12. So this doesn't really work. Here, my 5s can cancel, but 4 doesn't go into 13. But yeah, 4/5 and 5/13. But I'm going to just go ahead and multiply them because we're going to have to add them. Yeah. And I like the fact that I have 5 and 13 already. Why simplify something and then have to change it so I can add them back together? All right. I'm going to just erase that part there. So we have 12 times 3 is 36, so that's -36 over 5 times 13 is 65. And then we have negative times negative, so positive 20 over 13 times 5 is also 65. So now we can actually get our, this is positive 20. This would be -16. We have more negatives than positives over 65. This is the exact value of a sum of two angles given what we were given at the beginning there. We also have sum and difference formulas for tangent as well. Let's take a look at these. Again, sum and difference there. When it's the sum, you'll notice that the plus is on top and the minus is on bottom. And it's tan u plus tan v, 1 minus tan u tan v. When it's a difference, it's the same thing. Notice it's tan u tan v on top, 1 plus tan u tan v on bottom. But the only thing that really changes are the signs. So the sign here will always match what's on the top, and it'll be opposite of what's on bottom. So let's use that formula to verify this identity that we have with tangent. The tangent of pi minus x. And writing that out, this is the tangent of pi, and remember they match on top, so tangent of pi minus tangent of x, and then on the bottom we have 1, and it'll be the opposite sign plus tangent pi tangent x. So what is the tangent of pi? Well, tangent of pi, remember, is sine over cosine, and for pi, sine is 0. So that gives me 0 on top over whatever cosine is, it's -1. So, but 0 gives me 0. So that gives me 0 for tangent of pi. So that's 0 minus tan x over 1 plus 0 times tan x again. Well, 0 times tan x is just 0. So this gives me negative tan over 1 plus 0, which is 1, which is negative tangent of x. Oops, kind of lost the n there. Spell tax, nobody likes that. So tangent of x, which is what we have on the other side. The last thing we're going to look at here is the double angle formulas. We've looked at writing a formula as the sum. I'm sorry, not the formula. Writing an angle as the sum or the difference of two angles, right? So a addition statement or a subtraction statement, taking the sine or the cosine or even the tangent and writing it in exact terms if it fits one of our things. The other way we could is to rewrite or think of our angle as being double another smaller angle, something that might be known. And so, at any rate, we have several of them here. We see for the sine, we've got a formula, and there's only one. Twice the sine of x times the cosine of x will be the sine of 2x. So these x's will represent half of that, what we see here. And tangent 2x is twice tangent x over 1 minus tangent squared of x. And for cosine, we actually have 3 different formulas for cosine of 2x that we can choose from. All right, now let's take a look at the double angle formulas. And this is actually 5.3, but I already stated that. All right, so we're told that the cosine is negative 3/5 and theta is in the second quadrant. If theta is in the second quadrant, let's finish out the rest of that triangle. If I know it's negative 3 over 5, so that negative 3 would apply to the x, and hypotenuse is always positive. We have a 3, 4, 5 triangle going on. So if you have 3 and 5 for the hypotenuse, you know that the other side has to be 4. And 4 would be positive because it's in the second quadrant, and the y value is always positive in the second quadrant. So if we didn't know that, with theta or with cosine being negative, we could have either been in the second or the third quadrant. We wouldn't know, but we would have a negative sign. So it's good for us to know what quadrant we're in. In fact, we would need to know. All right, so for sine of 2 theta, this is going to be equal to twice the sine of theta times the cosine of theta. And we can, from our triangle, know what the sine is. That's going to be opposite over hypotenuse, so 4/5, and it's positive, times cosine, which we were told was negative 3/5. This is 2 over 1. 2 doesn't go into either of those 5s. 2 times 4 is 8, and 8 times negative 3 is negative 24. So we get negative 24 over 25 for twice that angle. For cosine 2 theta, remember that there's several choices that we have here. So let's go back. We had 3 of them here. We could use this one, very similar, very simple, cosine squared x minus sine squared x. Let's go back. So let's go cosine squared theta minus sine squared theta. That's what we had, right? I'm double checking. Cosine minus sine. So since it's subtraction, they have to be in the right order. So the cosine of 2 theta, cosine squared, well, cosine was negative 3/5, so negative 3/5 squared. Subtracting sine squared, well, sine was 4/5. So that's 9/25 minus 16/25. And 9 minus 16 is negative 15 over 25. I'm not sure where I got 15 there. It's definitely not right. 9 minus 16 is negative 7 over 25. Let's maybe try another one with cosine. Since cosine had several of them, let's say we wanted to do cosine 2 theta is equal to, what's the next one down? 1 minus 2 times sine squared. 1 minus 2 sine squared theta. And, okay, let's see what we get. This would be 1 minus twice, and sine of theta was 4/5. And we're going to square that. So this would be 1 minus twice 16 over 25, 4 squared and 5 squared. And this is 2 over 1, so 16 times 2 is 32 over 25. 1 then, writing it as 25 over 25 with that common denominator. If we subtract 32 25ths, we see 25 minus 32 also is negative 7 over 25. So we see that gave us the same outcome. We like that. Same outcome we like. So we could do the third one too, but we can just be confident, okay, they're not lying to us. All right, well, how about we take their word for it there? All right, what about the tangent of 2 theta? The tangent of 2 theta is 2 tangent x over 1 minus tangent squared x. 2 tangent x, 2 tangent theta over 1 minus tangent squared theta. All right, well, tangent, that is opposite over adjacent, TOA. So that's 4 over negative 3. So this would be 2 times negative 4/3 on top. And then 1 minus negative 4/3 squared on the bottom. On the top, that leaves me with negative 8/3. 8/3. And that's terrible. Let me make sure that's clear there. That's supposed to be a 3. And on the bottom, that's 1 minus 16/9, which 9/9 minus 16/9 gives me negative 7 over 9. With that, we can take the top, so negative 8/3, and multiply it by the reciprocal of the bottom, which is negative 9/7. This was negative. Negative times negative is positive, so I have 72. Actually, let's simplify this out first. This is 8/3, so 3 will go into 9 3 times. 8 doesn't go into 7, nor does 3. So that gives me negative 24 over 7. Negative times negative is positive, so we have 24/7 for my tangent of 2 theta. So we've learned how we can take things like the sine of 75, we can break it into a sum or a difference. We can take angles that we know, we can double them and still express them in very straightforward ways, exact ways, using the double angle formulas.